So, in this segment we will look at the remaining aspects of rheometry, where we try to use rheometer along with other techniques. And the first example is using dielectric spectroscopy. So, dielectric spectroscopy is very similar to the mechanical spectroscopy which we have discussed in the course so far, where we apply a stress or strain sinusoidally, and when we apply the stress, the strain or strain rate is the output. So, in dielectric spectroscopy we apply current or voltage, and based on the input and output we can then again analyze and then get an in phase and out of phase component. So, when current and voltage, of course, we also can talk in terms of current density and electric field. So, current density and electric field. Can you think of the analogous variable in the mechanical domain? So, generally when we do experiments we will measure current and voltage, but generally when we talk of material behavior we will say current density and electric field. So, similarly in mechanical domain, so this is what is in electrical domain. So, in mechanical domain what are so stress and strain are again not directly measurable. So, they are in fact analogous to current density and electric field. In fact, the material behavior is defined in terms of stress and strain, but when the measurement is done, what is it done with load and right. So, we generally will measure load and then displacement, load versus displacement curve we will say sometimes, right, or deformation. Deformation will still imply that we are processing the data and dividing by the original length, but displacement is basically what is being measured. And load versus displacement will depend whether, let us say I do a 1 inch diameter rod or if I do 2 inch diameter rod, because load displacement are not material properties, but they are actually dependent on the type of geometry which is being used. But stress versus strain property will not depend on whether I use 1 inch diameter or 2 inch diameter, because they are material properties. So, same way here when you do current and voltage discussion, it depends on the resistor dimensions or the capacitor dimensions and the area between plates in case of capacitor and so on, the diameter of the resistor and the size of the resistor and so on, but current density and electric field are material properties. So, generally just the way you can talk in terms of load displacement and say, or in terms of current and voltage, but more correctly when we describe material behavior we should talk in terms of current density and electric field. So, depending on whether current density and electric field are in phase or out of phase, we will have the energy storage and energy dissipative phenomena. So, do you recall from your earlier studies on electromagnetism as to, for a capacitor, how is current density and electric field related to each other, and for a resistor how is current density and electric field related to each other?
For resistors, it is inversely proportional to resistance.
No, resistance is the see. So, just in this case Hooke's law of the modulus or the viscosity are proportionality constants. So, similarly for electrical domain of course the capacitance or resistance are such proportionality constant. Remember again, capacitance and resistance are being measured in this domain, because it depends on the element itself. So, if I use load displacement and divide with load by displacement, I will get modulus, right, but that is not a material modulus, it depends on what size do I use. So, therefore, resistance is not really a material property, but resistivity is. Just the way modulus is material property, but load by displacement will depend on what is the size cross sectional area that I use, because load is, let us say F by A will be equal to the Young's modulus, right, which let us say we denote by E into the displacement divided by original length, right. So, displacement divided by original length, this is how stress versus strain is, right. So, depending on the geometry being used, the displacement load relation will change. So, if I were to define a coefficient, it will be E A by L naught into U. So, therefore, the geometry will determine, and in fact, if you remember current and voltage relationship, you similarly have the electrode area and the distance between electrodes coming into the picture along with dielectric constant. So, the dielectric constant is the material property which relates current density and electric field, while the capacitance is actually element property, just the way here also this is the element property, it is no longer material property. So, in just the way we talked about stress, strain and strain rate, here also we can talk of change of rate of change of electric field, rate of change of current density and current density electric field, and we can have materials which are both capacitive and resistive as we had visco and elastic. Capacitive will imply energy storage, right, and the resistive will imply energy dissipation. So, if we have a material which has the mechanisms by which it conducts or the mechanisms by which it stores energy, electrical energy, then we can do a dielectric spectroscopy on it, by which what we mean is we will apply current at different frequencies and then look at whether it is mostly capacitive or mostly resistive. So, for example, just the way we saw that there is a basic primitive model for viscoelasticity was Maxwell model, right, which said that predominantly viscous response at low frequencies and then elastic response. Then we saw also standard linear solid model, which was elastic response, which was rubbery, and then elastic response, which is glassy. So, for what we saw was G prime as a function of frequency was something like this. So, at very low frequency also you get elastic rubber elasticity, at very high frequency you get glassy elasticity, and G prime varied like this. So, if you look at the dielectric constant and the real part, which again denotes the capacitive or energy storage contribution, generally this kind of a behavior is seen for many materials, and this is called a debye relaxation in the material. Dielectric constant, remember, is the ability of a material to store energy. So, if I am applying, let us say, some constant, so this is again frequency. So, if I apply small let us say frequency, then what I am doing is I am giving material enough time for the dipoles to orient. Many of these debye relaxation processes are related to dipoles within the material. So, they orient, therefore, they store the energy. When the electric field is removed, they will come back, and therefore, the stored energy can come back. But when you go to very high frequencies, then this is not possible. Now the frequency is changing, the electric field is changing too fast, and the dipoles really cannot respond. Therefore, they do not store as much energy, and therefore, the relaxation time, the dielectric constant comes down. But there is some residual dielectric because there are some some other mechanism which can actually respond at very high frequency. So, therefore, there is small amount of dielectric material, dielectric constant is there. So, you can see that both dielectric and mechanical responses mimic each other in terms of the frequency response. Here also at very low frequency the segments can move, and therefore, we get rubber elasticity and very high amount of deformation is possible. At very high frequency, only with small deformation the material will break, but the modulus is very high because you require lot more energy for small deformation. So, therefore, from rubber to elastic, similarly here also if I go here I have more flexible behavior, here I have more rigid behavior. In the sense, in this case dipoles can orient, therefore, flexibility is there. In this case dipoles cannot orient, therefore, there is no flexibility. So, you can do both dielectric spectroscopy and mechanical spectroscopy simultaneously, and sometimes you can highlight changes which will affect dielectric properties more compared to the mechanical properties. For example, let us say if you have a polymer molecule which has let us say dipoles, and so if let us say there is a polymer molecule and it has dipoles, and these dipoles are all let us say arranged in the direction of the polymer, right. So, like this there are dipoles everywhere. So, when now this material is you are doing dielectric, when you are doing shearing, of course, we know that there are segmental motions, there is entanglement and all of these things which affect. Similarly, when you are applying electric field, how these dipoles are able to move will determine whether the energy will be stored or not. For example, if I take this polymer to melt, then I know that dipole orientation will be possible. But if I take this polymer to below glass transition where it becomes frozen, then the dipole orientation will not be possible. So, therefore, I can magnify the properties or simultaneously study two different aspects of the material behavior. In fact, one other thing you can do is, if you look at each and every dipole, if you add all the vectors together, in the end what you can do is you can get end to end distance, right. So, it is like saying that I have lots and lots of small vectors. If I add all of these vectors, then I will get my eventual end to end distance, and this end to end distance is based on addition of all these dipoles. So, by knowing how the dipoles are orienting in general, I can also have an idea about how the overall molecule itself is orienting. So, in fact, you can distinguish between reptation motion, which is the whole molecule itself moving, using dielectric spectroscopy. You will not be able to do that in what we did in all of our rheology was to speculate that since we observed viscous response, the relaxation time must be such that the overall polymer is reptating, which means entanglements are relaxing away and the whole polymer can move. But by looking at dielectric spectroscopy, you can in fact try to distinguish between two different frequencies, one frequency at which the overall polymer can move and the other frequency at which the polymer does not seem to be moving. And that is possible because dipoles are actually tracking the individual polymer motion, while when we are doing mechanical spectroscopy, we are just looking at bulk behavior and not really tracking an individual molecule. So, therefore, it is advantageous at times to do this simultaneously. Whenever you can try to highlight what is the, for example, if you have two components in the system and your suspicion is one of them is leading to viscosity increase, then what you can do, and you can hope that one of them is only responding, has dipoles. So, you can do dielectric spectroscopy on it also. If you see that the dipoles are also getting slowed down, then you know that whichever has dipoles is the one which is slowing down. But if you see that there is mechanically things are slowing down, but dielectric it does not slow down, then you know that the other component is probably responsible for the overall mobility decrease in the material. So, therefore, you can complement and do dielectric spectroscopy and rheology together. Magnetorheology, of course, is for those fluids which respond to magnetic field. So, many of the commercial rheometers these days will come up with these attachments where you can apply magnetic field at the same time do shearing, and for brake fluids or several such application, by application of magnetic field you can change the properties. For example, with iron oxide particles, you can, if you apply magnetic field, suddenly they will align and they will form a network and viscosity will be very high, and otherwise the viscosity is very low. So, you can manipulate the properties, and so for such fluids you may want to study the properties as a function of magnetic field. Rheo-microscopy is again a phrase in which you observe the material while you are doing rheology. So, as opposed to microrheology where we add the particles, if we just observe the microscopy of the particles itself. So, for example, we talked about a particulate gel. So, this kind of a particulate gel. So, if we view it under microscope, we may come to know that whether clusters are breaking or what is happening to the particles as we are shearing the material. So, therefore, rheo-microscopy refers to basically looking at microscopically the material while it is being sheared also. For example, one application could also be that let us say I have a capsule which is a liquid and liquid emulsion. So, let us say we have a liquid and liquid emulsion, and this is done by having, let us say, one fluid. So, again maybe let us say oil or some fluid, and then we have another fluid, but then separating these two we have a, so that is why it is called a capsule. So, there is a protective layer. So, this is a protective layer which separates, and now this emulsion is used as a product somewhere where it flows, it is forced to go through narrow openings and all that. And one question we may want to know is, under what shearing does this protective layer break down, right. So, what we can do then is to put this overall sample in the rheometer, start systematically shearing it, and at the same time try to observe microscopically. If we can see the overall capsules remaining, then we know that shear is not enough to break it, but we suspect that at some particular high shear rate, because what is happening is this fluid and its protective coating which is outside, when we subject it to shear, basically what we have is some part of the, because of the shearing we will see that the forces on the capsule surface will cause it to break. In fact, this is the principle which is used in recovering materials from a cell, biological cell, right. If you break the cell wall, then whatever are the contents inside can easily be used. So, in fact, you can shear it. If you shear it at high shear rates, then the cell wall will break down, then the internal components can be recovered. So, therefore, in such cases it becomes useful to do rheology, at the same time also examine under what condition the breakage happens, and so microscopically is done. Or if we have any colloidal system which are rod like particle and we want to know whether they are orienting, so we can again do microscopy along with rheology to see whether orientation is happening. So, there are several applications in which microscopy is done along with rheometry itself. And then other important aspect of rheometry in the last 5-10 years has been that we do not assume the flow, we actually examine the flow that is happening. For instance, we have been always saying that between two parallel plates, if you take the fluid, right, and we assume that because the top plate is moving at certain velocity, we will have a linear velocity profile. The only thing we are ensuring when we conduct experiments of this kind is that at the top plate velocity should be v and the bottom plate the velocity should be 0. So, if we look at there are only 2 points we are fixing, this point is being fixed, this point is being fixed. Now, one of the solutions to this flow problem is the linear velocity profile that we have solved, but can you think of situations where maybe linear velocity profile may not be valid, or can you think of what are the assumptions that went into so that we get the linear velocity profile? Suspensions, what would suspensions do? Because of suspensions, why would we not get linear velocity profile? So, what do we mean by instabilities? No, so secondary flows is one aspect. So, in that case what happens is we will still have one dimensional flow. Okay. So, let us, so if we have secondary flows, then what happens is there is flow in the other two direction. For example, we are generally mentioning that there is only Vx and we say that Vy and Vz is 0 in fact, right. That is the assumption that we are making. So, secondary flows, whenever we say, that means that Vy and Vz are also there. So, let us still assume that we are able to do flow where Vy and Vz is still predominantly 0.
Compared to top plate, velocity gradually increases.
Yeah.
If there is suspension, the increase will not be regular way.
Yeah, why? So, okay, that is one aspect that we always have to worry about. Given that whenever we talk of suspension, there is always heterogeneity in the material. By definition, material is heterogeneous. So, generally in such cases what we say rheometry is that the separation, right, the plate separation should be at least 10 times the particle size. Generally, if we are ensuring this, then the fact that there are local variations and because a particle is there or not there, all that will average out, and linear velocity profile is still very good in terms of giving us the bulk behavior of materials. So, generally we will still get bulk behavior even though the sample itself is heterogeneous at microscopic scale.
So what is the plate separation?
Plate separation is this, right?
Gapping between two plates.
Yeah, distance between two plates.
Can there be settling of the suspensions if there?
So, that is one possibility. So, in general of course, the sample undergoing some change, right. So, in this case let us say there is a settling of particles, then at the bottom plate they may settle, and but what will that do? If let us say particles start settling, we have a flow and then the more particles now below. So, effectively we have a situation where we have let us say more number of, so we will have some particles here, but here there will be more number of particles, right. So, what do we expect now the velocity profile to be?
The bottom plate.
Let us assume that if we were to have no settling like this, then the velocity profile would have been these 2 points are fixed, right. So, this would have been the velocity profile. So, what would you expect the velocity profile to be? The velocity profile would be lower than what is expected. So, let us say the velocity profile will be like this, it is very low, and then it increases linearly, right.
But the concentration of the suspension can
will also vary, yeah,
accordingly we can get
yeah,
parabolic variation or exponential.
yeah. So, this so what we are saying therefore is we are not no longer sure as to what the variation of velocity within will be, because the material itself shows certain behavior which leads to when we derive this we assumed material properties to be constant throughout, and so in fact we have this phenomena of what is called shear banding, where the flow breaks down into two domains. So, what we discussed was a case of where we have two domains, one where effective shear rate is low, while one where effective shear rate is high. So, two regions where one low shear rate region and high shear rate region. So, the flow has broken into two parts. So, that is why it is called band. There are two bands which have appeared. One question that always could be asked is, should we be measuring rheology of such materials when there is settling, because we in the end we would like to measure the properties of material themselves, and if there is settling involved, then clearly we are not characterizing the material, but the settling phenomena. So, therefore, one may argue that therefore, this kind of materials you should not really measure properties, because settling is a very significant feature, right. But in other case, if let us say for settling slurries itself we need to have some estimate of properties, then we must do such experiments, but we have to be careful that while analyzing our data we must know that the overall flow is not really what is assumed, which is linear velocity profile. Then best way to look at this is through flow visualization, and again in this case also what we can do is we take the overall material of interest, and this overall material of interest we again put let us say one small set of particles, and as again using laser and scattering we can follow how these particles are moving. If they are and we can measure the velocity that way, and if we see that the velocity is what we expect in terms of linear velocity profile, then we say okay, there is no artifacts in terms of flows being different than the linear velocity profile, therefore we can do analysis. But if there is a we using the particle motion we find out that some particles are moving slowly while some other particles are moving fast, then we have basically a banding in the material. So, in general it helps to do flow visualization and examine what is the type of flow which is being observed between the in the rheometer geometry as opposed to what is the assumption. This is a steady state profile, right. What we are talking right now is a steady state profile. So, generally yield stress material, what you might see is, so let us say we have an yield stress material and then we start at time t is equal to 0, we start the flow, right. The top plate moves with velocity v. So, what will happen generally in such case is, since the top plate is moving now and the material which is at the top would have undergone the yield, and then the rest of the velocity will be 0, right. And then slowly as time goes on, more and more material will undergo yield and more material will start moving. So, that is the difference, but at again the steady state what you would see is generally, provided the shear stress that is being applied is higher than the thing, then you will again see a linear velocity profile.
So, but how do you know that the full?
So, that depends on what is the velocity with which you are applying, and therefore, what is the stress being applied on the material. See, let us say given that you are expecting some part of the material to flow, that means the stress is higher than yield stress, because if you remember, if you look at the linear momentum balance or equation of motion for a parallel plate geometry, the Gavani equation says, let us say in this case it is tau yx by del y is equal to 0, which means tau yx is constant. This is by there is no assumption involved in terms of which type of fluid, it can be viscoelastic, it can be just viscous. So, this is a Gavani equation for all materials. So, therefore, if some part of the material is yielded with this stress, other part will also yield. It is just that it takes finite amount of time for the yielding process to go. So, at steady state you would again expect a linear velocity profile, and what we are talking here also are steady state profiles only. The fact that most fluids will take a finite time to come to a steady state is an also important property, but generally we in rheology when we assume that that time is much shorter than the time for which we are examining the material properties. For example, we will assume that maybe it takes milliseconds or hundreds of a second to actually reach the steady state, and everything that we are examining is the material behavior itself. So, there are class of materials which show some density gradients like what we saw in case of particle gradients. So, whenever such gradients are possible, it shows shear banding phenomena, because the material overall breaks into a low viscosity and high viscosity material regime, and therefore, it breaks into a high shear rate and low shear rate regime. So, for examination of shear banding or any such features in rheometric flows, flow visualization is done, and there are multiple ways. So, what I explained was right now using optical method, that you put particles, and this technique is called particle image velocimetry. Basically measurement of velocity using images of particles. So, this is a fairly popular technique which from aerodynamics, which is a fairly large scale phenomena, to rheometer flows, which is a small scale flow. You can examine the overall flow profiles in detail at a plane using particle image velocimetry. Yeah, a region of interest can be looked at. Basically what you do is you take pictures again of a specific region and look at how particles are moving, and again by doing image analysis you can find out what is the velocity. Again the assumption is the particle addition is not doing anything to the fluid that is under study, because the amount of particles that are being added is very small. Of course, additionally the particles that are being added have the same density as the surrounding fluid, so that they themselves do not have any inertia, they themselves do not settle down and so on, they actually follow the fluid faithfully. So, therefore, by looking at their motion we get to know what is the fluid motion. Similar measurements could be done based on NMR or any other spectroscopic measurement, which is basically related to how molecules are moving at the molecular scale, and based on that you can then try to measure what may be the velocity. So, there are several such techniques which are available to capture the velocity of the material, and so all of this is called flow visualization. And then in terms of rheometry with scattering, we always would like to know information about structure of the material. So, depending on the length scale of the structure, we can use either light or X-ray or neutron to probe different length structure. For example, if particles are large and they can be seen using microscopy, then we do not even need to do any of these. But if particles are smaller, then we can look at light scattering and then get to know about what is their position, what is their orientation and so on, and therefore, what is the microstructure of the material. If they are still smaller, then we can do X-ray or neutron scattering. And so, using these scattering techniques, we will get to know about what is the length scale, dominant length scale in the material, and hopefully that we can relate to either a cluster of the particles, or in case of macromolecules a region where macromolecules are either crystalline or amorphous and so on. So, depending on the variety of how the scattering of light, X-ray or neutron happens based on the microstructure, we can find out. And most often we know that when we do rheology, we are shearing the material and shearing affects microstructure. So, quite often we come up with this hypothesis that under shear things may be getting oriented, under shear cluster may be breaking down, under shear orientation of molecules may happen. So, therefore, it is important to do this scattering along with when shearing is going on. So, many of the neutron scattering or X-ray scattering equipment or light scattering equipment can allow a small shearing cell to be attached on them. Alternately, these days rheometers also come up with attachment where you can attach X-ray scattering or light scattering, or neutron scattering is of course very difficult because you need the neutron beam, which is only possible with a nuclear facility. So, therefore, the neutron scattering attachment is not available, but X-rays can be generated in labs. So, therefore, X-ray scattering and light scattering attachments are available with commercial rheometers also, and neutron scattering is usually done with a rheometer or a shearing cell attached wherever there is neutron beam availability in a nuclear facility. And then to finish, there are some specific cells along with rheometers which come for extreme measurement conditions. For example, if we are dealing with oil and gas exploration, we have to deal with very high pressure phenomena. So, therefore, high pressure rheometers where you can apply extremely high pressure and then measure the properties. For example, water viscosity at the sea subsurface is very different compared to what we know of it as 1 centipoise, because the pressures we are talking about is like 3 kilometers of water column above it. So, pressure is extremely different, and under those conditions in fact viscosity will also be a function of pressure. And so, such properties, whether high temperature, when we have ceramic materials and their processing temperatures are 1500 degrees Celsius and so on. So, there are high temperature attachments also for measuring the viscosities of materials under those conditions. There is also of course, you can use some other rather than looking at purely mechanical, sound interacts with material and you can get to know about mechanical properties of the material through this interaction. So, for example, sound is nothing but pressure waves. So, how pressure waves travel through the material is dependent on the elastic modulus of the material. So, therefore, by using ultrasonic probes, and if you use a vibrating probe, then you can then again do calculations and try to find out what are the material properties. So, this is usually done at high frequencies, because mechanical instruments have upper limit of generally hundreds of hertz or hundreds of radians per second, beyond which they cannot go. One last aspect sometimes is very thin film rheology. For example, when we eat something, the final feel that we get of the material being very good or bad will depend on a very microscopic layer and how it is sheared within our mouths and what kind of feel do we get. Do we feel it is rich, do we feel it is sticky, so that will be very different. Something which is very sticky we will say, oh, it does not feel good, but something which nicely shear thins and flows at the same time gives us, when we first take the bite, it gives us a rich feeling, but then it spreads very nicely and disappears in the mouth, we will say it melts in the mouth. So, then it is actually, so that thin film rheology is sometimes also extremely important. The first bite, second bite is just gives us a preliminary idea, but it eventually what happens. So, therefore, in such cases you may want to understand the flow behavior of material when they are micron thick, while most of our rheology measurements are hundreds of microns, at least 50 microns and higher. So, therefore, but the problem with thin gap rheometer is the material structure is again the same order of magnitude as the gap itself.